Okay, in this video we're going to look at the calculations involved with radioactive decay. Now that we understand how to determine if an isotope is radioactive, how to determine what type of decay it's most likely to undergo, and how to determine what isotope is remaining after the decay, the last thing we need to look at with this decay idea is the math, the calculation. So remember, radioactive decay is one reaction or process that results in the emission of either a beta particle or alpha particles along with gamma rays, and the creation of some kind of new isotope. But just because we have one reaction that releases an alpha particle or a beta particle doesn't mean that's the end of the story. Many times, radioactive isotopes will have a series of these decay processes. So these are decay series, more than one decay process. So if we look at this example, this shows uranium-238 undergoing an alpha particle decay to thorium-234, then a beta particle to palladium-234, then beta particle to uranium-234, and then a series of alpha particle decays, because each of these isotopes in between is still unstable. So until it hits a stable isotope, it's going to continue to decay and release alpha or beta particles. And this series shows several reactions until it gets down to lead-206. This is the first stable isotope it reaches. So uranium always eventually ends up being lead. Alright, this particular decay series is not necessarily the same for every uranium-238. For instance, it can do beta particle first before it does alpha particle. This is just one example of a series that it could go through. So when we look at doing calculations for our decay rate, we need to remember that this is very similar to our kinetics for every other type of chemical process or reaction. And it even follows the same type of kinetics that we've already looked at. All radioactive isotopes follow first order kinetics. So remember our first order kinetics, our same kind of equations that we've used before. Alright? All we're doing is changing some of the vocabulary, changing some of the symbols, but it's still the same idea. Decay rates are normally measured in terms of activity. So this funny A here represents the activity of the isotope, or how much radioactive activity we can expect from it. And that is proportional to the number of nuclei it has. Alright, so activity is equal to negative here because we're decreasing the amount because it's a reactant. The change in the number of nucleides, or how much you have, over the change in time. So the activity is based on how much we have. When we look down here then, activity is proportional to the number of nucleides we have. Since this is very similar to what we've seen before, where rate is equal to k times the amount of a to the first power, this is where we get the idea that this is first order. Rate is proportional to the amount. As the number of nucleides decrease, the amount of activity we get also decreases. Because this is first order, we also can follow the half-life rules. So remember, half-life for first order is only dependent upon the k value, ln of 2 divided by k. This also means that we have a curved line when it comes to our decay process instead of a linear relationship. But this means our half-life is constant. If you remember from our half-life equations, the half-life for first-order reactions is the only one where the half-life remains constant no matter the concentration. It's not dependent upon concentration. So we have constant half-life for different isotopes. This is an example of carbon-14, which we know the half-life is 5,730 years, so every half-life is exactly that same length of time. That allows us to use carbon-14 as a dating type of isotope, and we'll talk more about that later, because it's predictable how long it takes to get down to different levels or percentages of original amount. Now, because we're using first order, there's another type of equation we can look at dealing with the number of half-lives. So N here is the number of nucleotides we have at a certain time, is equal to our initial amount of nucleotides times 1/2 raised to the n power, where n is the number of half-lives our decay process has been through. Alright, so if we know it's been through 4 half-lives, we can put in 4 for our exponent, our initial amount, and we can determine how much is left. So let's try this out. Barium-122 has a half-life of 2 minutes. We originally have 80 grams of our barium, but it takes us 10 minutes to set up our experiment. How much barium are we going to have left when we actually start our experiment? Alright, so the first thing we need to do is calculate how many half-lives it's been through. If we're going to use this equation, we need our exponent. So it took 10 minutes to set up. This is the amount of time that's elapsed, divided by the half-life, which is 2 minutes, means it's been through 5 half-lives. Alright, so we need to know how much is left. We started with 80 grams, our initial amount, times 1/2 to the 5th power, because it's been through 5 half-lives. Alright, so we can now solve for NT. So 1/2 to the 5th power times 80 grams means we have 5 halves left, or 2.5 grams. Alright, so if we start with 80 grams, 1 half-life gives us 40, 2 half-lives gives us 20, 3 half-life gives us 10, 4 half-lives gives us 5, and the 5th half-life gives us 2.5. Alright, let's try one more. We start with 10 milligrams of iodine-131 as a medical tracer. How much is left after 24 days if the half-life is 8 days? Alright, so again, we're trying to do our NT. We started with 10 milligrams times 1/2. Okay, what is our N? How many half-lives has it been through? Well, 24 days divided by 8 days, which is our half-life, means it's been through 3 half-lives. Alright, so we have 1 divided by 2 to the 3rd power times our 10 gives us 5/4, which is 1.25 grams. Alright, we can do this again by counting by half-lives. So we started out with 10, so 1 half-life would bring us down to 5. 2 half-lives would bring us down to 2.5. And then the 3rd half-life would bring 1.25. Alright, so just to familiarize yourself with the equations, These are the same first order reaction equations we've already seen. We just have some different types of variables thrown in. Don't let that confuse you. For radioactive decay, we can either look at it in terms of nuclides that we have left or that we started with, which is how we did the last equation, the last questions, or we can do it in terms of activity, which will be measured in activity units. Alright, so activity units for radioactive decay. A little bit strange to look at. SI unit for radioactivity is a becquerel, or a BQ, which is the same as 1 disintegration per second. So sometimes you'll see it as disintegrations per second as well. Also, the unit called the Curie, or CI, has been introduced, named after Madame Curie. And this is based on 1 disintegration per second of 1 gram of radium, which is the isotope the element she discovered. So 1 Curie is 3.7 times 10 to the 10 disintegrations per second, because that's how many we have in 1 gram of the radium-226. The point here is that don't let the units confuse you. The units are just measuring activity. Disintegrations per second is just a unit. Alright, Curies and becquerels are just units. So we still want to use our integrated rate laws from first order kinetics, and this is just shown in different ways, either with the number of nuclides or the activity. Half-life equation is still the same. Alright, so let's look at some examples of how to do the radioactive decay. Alright, sodium-24 has a half-life of 15 hours. Initially we have a specific activity, 2.5 times 10 to the 9th disintegrations per second. How much activity is present after 7 days? Okay, so we're looking at this in terms of activity instead of amount, but we're going to use the same equations. So first order is Ln. We have activity initial over activity final equals K times T. So still using the same first order rate laws. So we're going to fill in what we know. Right now we have an initial amount of our activity. We're trying to find a T, and we know we want to look at 7 days. So not only do we need to find a T, we have to find K first. And how are we going to find K? Let's go back to the first sentence. It told us the half-life. Remember half-life for first order is ln of 2 over K. So since I know the half-life is 15 hours, I can calculate K. So we're going to do that first. So we have ln of 2 divided by 15. Our K is 0.0462. And this would be 1 over hours because I used the half-life in hours. Alright, so now let's fill in what we have. ln 2.5 times 10 to the 9th disintegrations per second over what we don't have, or how much we want, equals, here's our K value. Now since my K is in 1 over hours, I have to have my time in hours as well to make the units match up. So this is going to be very important. Whatever your units for your T has to match up with your units for K. So K is in 1 over hours. So how many hours in 7 days? Alright, so 7 times 24, 168 hours in 7 days. Alright, so now we can multiply the right side. It's 0.0462 times 168 gives me 7.76. Now the left side of my equation is the ln of a ratio that contains my variable. So we need to get rid of the natural log. We do this by using base e. So if I raise both sides to e, I have 2.5 times 10 to the 9th over my variable is equal to, alright, so over here I'm going to do second ln to get the little e. Alright, 2348.66. And then my variable's on the bottom, so I can cross multiply. I can multiply this over and then divide, which is normally what I do, in order to get the value. Alright, so 2.5 times 10 to the 9th divided by our 2348.66. 1.06 times 10 to the 6 disintegrations per second. So again, we're looking at activity, which is going to have the same units that we did up here for our initial activity, disintegrations per second. So we should see that our activity decreases over time, so we have a smaller number than what we started with. Alright, let's look at another example. How long will it take a radioisotope to decay to 40% of its original activity? The rate constant is 0.055 1 over s. So percentages come up pretty often in radioactive decay. Instead of looking at grams or activity, they look at percent remaining. But we can use this the same way. So again, we're still going to use our integrated rate law for first order. And instead of finding grams or activity, we're going to be using our percentage. So remember, 40% means 40 out of 100, or if you prefer, 0.4 out of 1. Okay, and so we can use those ideas when we look at putting them into our equation. Alright, so ln, if we're looking at having 40% remaining of its original activity, what percent was the original? Okay, we always assume the original was 100%, and we want to know having 40% left. Alright, and we have our rate constant, 0.055, and we're trying to solve for time. How long is it going to take? Alright, so our percentage then, we started with 100%, now we're down to 40. How long did that take? Alright, so 100 divided by 40, we want the ln of that. So this is 0.9163. And then we're going to divide by our k in order to find time. 16.66. And because our k was in 1 over seconds, this is going to be in seconds. Alright, let's do one last example with this. And let's see if we can figure out how we would solve this. Alright, technetium 99M used in brain scans. If we get 200 grams of the isotope, after 24 hours, only 12.5 grams are left. What is the half-life? Alright, so what's the best way to approach this? So for half-life, we need K. Alright, so we can think of doing half-life In order to find half-life, we'd have to know K. So we'd have to do integrated rate law to solve for K. Alright, the other equation that we've looked at doesn't contain K at all, so that would get a little bit more complicated. So let's do this way. Let's find K using our integrated rate law and then plug it in for half-life. Alright, we received 200 grams of the sample, so that's our original amount. After 24 hours, we only had 12 and a half left. Alright, so we'll plug that in. Let's find K. Alright, our left side is a real number, so we have 200 divided by 12 and a half. ln of that. So 2.773 equals K times 24. So we're going to divide by 24. 0.1155. This would be our K value in terms of hours. So 1 over hours. And we can plug that in over here to find our half-life. Okay, so ln of 2 over 0.1155. Whoops. Let's try that again. ln of 2 divided by 0.1155 gives us 6 hours for our half-life.